Well, thank you, Leslie, and thank you for all your great questions today. It was a real pleasure to have such a degree of engagement in terms of asking questions about what works and what doesn't, and also trying to understand how we can go forward sustainably with approaches that can actually work. So I would encourage us to participate interactively. I'm a firm believer in the inverted classroom, and by that, we've seen a couple of small lectures in the form of videos so far, but now we have an opportunity to interact with this material, and so I would encourage you to ask your questions as we go along, because I think that can facilitate the discussion really effectively. So thank you for joining us today. Recently, I did a session for a group called REX, and it stands for Relationship. Our carbon footprints are normally a depressing story about how many gigatons of carbon we've emitted over the past 200 years. And it can be very daunting, it can be very depressing, it can be very demotivating. And I've seen this story time and time again. And recently, what we've come up with and what I've learned about are not only talking about our carbon footprints, the 10 countries that have emitted the most carbon historically in the world are mainly Western countries. Of those 10 countries, only 2 countries have not put a price on carbon. And they are Russia and the United States. So we're in a tie for dead last. But we have an opportunity to change that. And I'll talk with you a little bit about how that can enter in today. But carbon handprints are much more positive. And the way I think about carbon handprints is how can we take positive action and guide by example to actually make a difference in our lives at the gigaton scale. And those are the kinds of projects I'll talk with you about today. And that is, what can we do that's effective, entrepreneurial, and can make a significant dent in restoring carbon balance. So that's what I mean by carbon handprints. I recently ran across this amusing photo of what I imagine to be the New York subways after, which hurricane was it? Sandy. And my good friend John Englander was for a couple years corresponding with me about his book called High Tide on Main Street, which came out 6 weeks before Sandy. You couldn't ask for a better advertisement. And what I find time and again is that when you're on the right track, things like this happen. In other words, his book came out 6 weeks later, the New York City subway became a scuba diving event or situation. And you know, for better or worse, John Englander was then doing the book tour circuit because it was so popular to try to understand how these issues are hitting home.
I've seen a picture similar to this that I understood was faked.
This one's fake. It's definitely fake. The point is really to be understanding what are the issues. I saw a slide in the last couple of weeks that said with expected sea level rise over the coming century, we're looking at annual costs in New York City that exceed about $3 billion a year in terms of infrastructure, and in other cities like Mumbai, Bangladesh, China, $6 to $12 billion per year in terms of the cost of increasing sea level. So these are issues that are measured in billions and trillions of dollars. And the key question is, how can we monetize these opportunities? Partly because that's the way our entrepreneurial system works. But part of it is, how do we connect from the billions of dollars a year that reinsurance companies insure to something that we can actually do to restore climate change? So one of the things I'll mention briefly today is reinsuring the reinsurance companies, because that's something we can do with some of the technologies we're talking about. And it's these kind of couplings to our capital system that really make a difference. One of my advisors at Caltech, Carver Mead, said that companies are the engines of creation. They are the vehicles by which we scale. And it's that intersection of engineering, entrepreneurship, and climate change that give us the tools to actually make a difference in this world. So that's the theme behind what we're doing. Did you have a question? Yes?
No.
Okay. So we started nearly 10 years ago. And 10 years ago, we went to the International Coral Reef Symposium, where there were 1,000 coral reef biologists lamenting the demise of their coral reef ecosystem. It's estimated at the Australian Institute of Marine Science that this century, the Great Barrier Reef will become a geologic relic. Already, we've seen calcium accumulation rates drop 13% since 1990 in the coral reefs. And this year and last year, we've seen 50 to 90% coral bleaching in the reefs off Hawaii and these reefs off American Samoa. I never thought I would see Hawaiian coral reefs bleach in my lifetime because it's cooler water. It's a lot cooler than American Samoa. But we did it. It happened last October, 50% coral bleaching. So a very serious situation. This year's El Nino is expected to produce similar coral bleaching levels. And this is very serious. You know, corals live within 5 degrees of mortality their entire lives. And so they are the canaries in the coal mine. They are the ecosystem that's living on the edge and are the first to go during major extinctions. Now, there have been 5 extinctions on Earth, mass extinctions, in the history of the Earth. And they, each and every time, were preceded by the demise of the coral reefs. The 6th one, they're calling the Anthropocene, which is the notion of imperiling half the species on Earth, this time at the hand of man, due to catastrophic climate disruption. And it's a real challenge. The front line here are these coral reefs. And so one thing we did back in 2008 was to embark on an effort to see if we could reverse coral bleaching on the coral reefs. And what we did, with a limited amount of support by private foundations, was that we organized a system. We flew down to American Samoa, and we managed to experimentally cool off a small region of coral reef by 1 degree Celsius. And we expected, and then we sat and waited, expecting it to maybe take a month for some of these corals to come back to color. Well, in less than 24 hours, these corals returned to color, and very intensely. And it was an amazing result. Now, what is the scaled version of this? We've been working for the past 5 years with the Honolulu Seawater Air Conditioning Company, which next year will be commissioning a 100 megawatt deep seawater air conditioning system for half of downtown Honolulu. What it's going to do is run chilled water through the streets of downtown Honolulu to all of the high rises, and those high rises will get their cooling water not from shipping fossil fuel 10,000 kilometers, burning it so you can produce electricity so you can run your air conditioner. You can imagine how many efficiencies there are in there. But instead, pumping deep water up from 500 meters down at a temperature of 44 degrees, running it through a titanium heat exchanger, exchanging 100 megawatts of heat, and then outfalling at 56 Fahrenheit. Now, what's fascinating to me is after all that process is done, they have 150 megawatts thermal left over going back to the sea. And the plan that we have is to actually seasonally utilize that 150 megawatts thermal to seasonally cool kilometers of coral reef and reverse bleaching or prevent that bleaching from occurring. Leslie.
So my understanding is it isn't just temperature, it's also ocean acidification. But you're saying bringing back temperature alone has a phenomenal effect.
It has an enormous effect. There's been a lot of press on ocean acidification, and it's an important effect and it's real. But when we're looking, let's say, triage on the operating table, and we're looking at corals, the reason they're bleaching today is thermally induced photobleaching. The high temperatures make the coral polyps and the zooxanthellae inside of them sensitive to light. And so that multiplicative combination of high temperature and light causes the bleaching to occur. The bleaching means they're on life support. They've lost 80 to 90% of their food source, namely the zooxanthellae, and they're living on life support. They have little tentacles like barnacles do, and they can try to eke out a living on clear coral water, which doesn't have much plankton, to try to scrape out a living and survive. But they've stopped producing calcium. They've stopped laying down additional corals. They have a compromised immune system. Half the time they die from disease. Other times they can be taken over by macroalgae, and sometimes they can come back. But what's typically happened is we've seen a binary decimation of the coral cover each time you get a major bleaching event, and they will go along at the lower level for a few years till the next hurricane comes or the next bleaching event happens. And so you're losing by binary factors of 2 each time. And you look at the Caribbean, you've gone from the 1970s, where I went fortunate enough to go diving then and seeing coral cover in the 30–40% range, down to today where you see coral cover in the 5% range. The US Virgin Islands are another example of this. Jamaica again, also, where it's been taken over by macroalgae and we've lost a lot of the corals. So it's a really critical issue, partly because 1/4 of all marine species spend some time of their life cycle on the coral reefs. These are the nurseries of the oceans. And what we found time and again is when you collapse one ecosystem, it cascades onto the next ecosystem. The pelagic fish, the shorebirds, the marine birds. There's a collapse of ecosystems. So our system to cool coral reefs is a Band-Aid. It's an attempt to keep a slice of this marine ecosystem alive at a time when we're losing thousands of square kilometers. And that's very depressing. But the thing that gives me hope is that coral reefs can come back, and if we can use the Band-Aid during the difficult decades to come, we can rebalance our carbon budget and we can actually get these coral reefs back to productivity. The key is to have a big enough section of coral reef, a big enough high-value reef, that they can continue reproducing within that zone. And that's the vision behind the coral reef cooling. This is big enough to do things on a kilometer scale, and what we prove here, we can take to Guam, and the US Navy, I'm happy to say, has adopted our suggestion to utilize deep sea water air conditioning for their marine bases, their Air Force bases, and their Navy bases. 40 megawatts of cooling on Guam next to really high-value reefs. So we're looking at being able to build in the infrastructure now that can actually make a difference and preserve high-value reefs in the Coral Triangle. So that's part of the philosophy behind where we're going with this. There's another event that I have to share with you because it blows me away and it's very, very poorly understood. What if I told you that there was a single plant in the history of the Earth that historically and single-handedly pulled 3,000 parts per million CO2 out of the atmosphere in less than 1 million years? How many people have heard of Azolla? Show of hands. 1 or 2. There was this event, and it's on Wikipedia, look it up, the Azolla event 50 million years ago, where one plant, all by itself, in the Arctic Ocean, right near the North Pole, pulled 3,000 parts per million CO2 out of the atmosphere single-handedly in 800,000 years. To me, this is a positive outlier. This is what I look for in nature. When nature does something without our interference at all that solves our problem, this is what we have to listen to. Azolla is an amazing plant. It's this tiny little plant like this. And what makes it so effective is that it's a symbiosis between the plant itself and a cyanobacterium that lives in the plant, produces omega-3s, fixes nitrogen, does all sorts of wonderful things. This plant is an aquatic fern. It grows 10 centimeters thick on the top of fresh water. How did it survive in the Arctic Ocean? 2 reasons. 1, the Arctic Ocean was closed, not open. Very limited circulation. Secondly, ambient temperatures were 20 to 30 degrees Celsius. And thirdly, you had phosphate pouring out of the rivers into the Arctic Ocean. So what happened? Near the river mouths, you had Azolla growing, taking all the phosphate it could, and growing. And guess what? The doubling time of Azolla is 2 days. Can anyone say lily pad problem or lily pad solution? This is incredible. So the idea of Azolla blows me away. Every summer, Azolla would cover the Arctic Ocean. How? The Arctic Ocean's salty. But what happens is the Azolla grows out over the Arctic Ocean, and as it does so, it keeps the waves down and keeps mixing down, and the fresh water creates a lens on the surface, propagates through the Azolla, and creates more fresh water on the surface. So it keeps growing and growing. With a doubling time of 2 days, this is why we have to harness biology to solve the climate problem. Biology has been fixing carbon for 3 billion years. We have to learn from the past and learn from nature to understand what natural systems we can leverage to sustainably sequester gigatons of carbon. It's my ambition, my personal ambition, to sequester a gigaton of carbon in my lifetime, or at least a gigaton of carbon dioxide, or cause it to be sequestered. And all of us, I believe, should have this ambition. It is doable. It is doable to create businesses successful, sustainable businesses that can actually do this, and it's the key to sustaining the planet that we live on. So, can we mimic Azolla? Can we find an opportunity to do this? What happened with the Azolla? Every summer, an Arctic Ocean, 1 million square kilometers of Azolla would grow. And every fall and winter, 1 million square kilometers of Azolla would die and sink to the bottom. And what's fascinating about this is that the Arctic Ocean, we know, was anoxic in the middle and deep. And so that Azolla would sink and go into the anoxic depths with no oxygen, where it would be turned into the Alaska oil that we find today. And that was 50 million years ago. Now that simple system, in less than 800,000 years, pulled down 3,000 parts per million of carbon dioxide. We would be happy to do 1/30th of that. That would take us back to 350. So it's an incredible opportunity. And I look at places like the Santa Barbara Channel, the Black Sea, and other places that are already anoxic at the bottom, in the middle. And I think, how can we harness something like Azolla to ensure food security, avert food riots and water wars, and yet at the same time sequester this scale of carbon? These are the kind of natural positive outliers that I look to actually do this. And in my engineering work, there's this notion of a positive outlier that I think we all need to understand and learn. I learned about it because I heard about a doctor that went to Vietnam after the Vietnam War, and people were starving. The children were starving. Everybody was starving and dying because there wasn't enough food. And the doctor went down there, and it was just disaster story after disaster story in all these places. But there were a few confusing positive outliers. There were a few children that weren't dying. There were a few children that were actually doing better. And he went and studied what these positive outliers were. And what he found was the kids that were surviving were getting 4 half cups of rice per day instead of 2 cups of rice per day. And they were getting little bits of crab shell and shrimp shell that were normally reserved for the adults. And these 2 tiny practices were enough for them to accumulate protein and body mass rather than losing it and dying. And so that ended up transforming the operations and recovery efforts in Vietnam, and the net result was that millions of children survived rather than dying. These positive outliers is what we as engineers need to seek in our basic science, in our engineering, and our research to find sustainable ways to actually save the planet. And I think Azolla is one of those examples. And I would love to work with all of you to figure out how do we harness technologies and plants and organisms like Azolla to restore food security, restore carbon balance on land, and get the carbon back where it came from, and that is in the soils and the seas. Question?
I want to make a call out too. I believe you spoke about this in the link that you sent us with questions and answers as well. So if anybody hasn't checked that out, there is so much valuable information in there. And your tie-in with cyanobacteria takes us back a couple lectures to our microbiologists as well. So this is profound. Yeah, definitely check out the link. And you're willing to correspond further on the link, I think.
Certainly. I would encourage people
resource
to add comments to the Google document that we're accumulating with questions and answers. And I think that's a great way to continue the dialogue online as well as offline. And so I think that would be great. Would encourage that very much. And that's not the last we'll hear about cyanobacteria, because they'll enter into the marine permaculture concept as well later in the session. So I look forward to doing that. So just in the last 2 weeks, I managed to read Tim Flannery's Atmosphere of Hope. And I'm fortunate enough to be able to see him tonight in San Francisco. So if any of you have questions for him, I will be happy to relay those. What impresses me so much about Tim is that he has collected the world's knowledge about what we can do sustainably and has organized it into this book and is actively working on solutions that are practical, that work, and are sustainable. And he's classified all the things we can do into 3 categories. The 0th thing in my mind is reduce carbon intensity. I mean, number 0 is to actually take public transportation, reduce the intensity of our transportation, move our electricity infrastructure into low carbon intensity approaches as well. And I will cite to my good friend Amory Levins, who has written Reinventing Fire, and that book is a prescription for carbon reducing. And it's talking about the four ways, the four major areas where we can actually reduce carbon intensity and go to, well, he likes to say, a $5.5 trillion net present value to being green, which fundamentally is about moving quickly toward and accelerating our progress towards fully sustainable practices so we can reduce the carbon intensity of our civilization. Now that can take care of 80% of it. And the question is, how do we actually go carbon negative, or I like to say climate positive? How do we go climate positive? These are the approaches that can actually pull carbon out of the atmosphere. Because even if we stop today, as you know, we're at an effective greenhouse gas level of 430 parts per million today, and it's increasing. And the challenge is, can we keep below 2 degrees Celsius warming? Can we do all these things? So Tim talks about 3 ways. The first is adaptation, and that is get used to it, although I'm not sure that wearing a scuba tank in the New York subway is the right way to adapt. But adaptation is one approach. It's a problem for cities like the town of Kivalina that were mentioned in this Arctic area, and that's one of the cities that we're actually working in. It's a problem in many of those areas. And how do we say adaptation to 100 million climate refugees in Bangladesh and China, not to mention India, and how about the $11 trillion in real estate in the Gulf Coast and the East Coast of the United States that's at risk from sea level rise? So adaptation has a very high price tag. The second is geoengineering, and you've heard some areas of geoengineering. As I wrote in our question and answer session, I view driving our SUVs around and taking high intensity carbon flights as acts of geoengineering. Why? Because we know the outcome of business as usual. We know what's going to happen with the coral reefs. We know we're going to collapse these ecosystems. We know that we're at the cusp of the Anthropocene, which is that we're actually wiping out species faster than we ever have before. And that's the kind of legacy I would hope that we could leave to our children, the legacy of leaving the planet with as many species as we arrived, because that's irreversible. And this notion of the Anthropocene, there's 7 million species on this planet that can't vote. And it's up to us to protect those species and protect that diversity. And partly because half the medicines we get are coming off the coral reef, or they're coming from biological metaphors. And we're just reaching the quantified century of biology this century. So to lose so many species right at the cusp of understanding them, to me, is a real tragedy. And so that's a challenge and an opportunity. I like to think of some of the techniques that have been talked about in this course as reverse geoengineering, because we're trying to undo some of the damage that's been done over the last 200 years. And especially when we talk about the third way. I mean, there are the techniques of using sulfate aerosols. There are the techniques of trying to, it's almost like window dressing, right? Because you can cool off the Earth, but you can't reduce the ocean acidification. Now, in this decade and next decade, it's temperature that's really critical in killing the coral reefs. But ocean acidification is affecting diatomaceous plankton, and it's affecting plankton that require calcium for their, and silica for their operation. And it's going to be a much bigger problem in the years ahead. So the third way is what Tim characterizes as pulling oxygen out of the atmosphere. And I will say that can be done biologically, chemically, and physically. And finding effective approaches that can sustainably pull the carbon out of the atmosphere and leave it out of the atmosphere and put it into seas and soils where they're stable for hundreds to thousands of years. And the United Nations has in their program, if you can keep the carbon out of the atmosphere for 100 years, you get a carbon credit. That's under the Kyoto protocols. So with that in mind, that's a long enough time scale where the United Nations has actually endorsed this approach. And so we have to look at how we can do this sustainably and profitably, particularly in a time where we don't have a price on carbon and we have relatively inexpensive fossil fuels. So it's a difficult challenge to understand how can we address this. But I'll talk about several approaches. Tim discusses 2 of these in his book, and one of them are actually storing carbon dioxide in marine sediments. Now, I thought this would be almost impossible, but Tim, in his book, discusses something that is in fact sustainable. Did you know that carbon dioxide is compressible? In fact, it's far more compressible than seawater. So much so that if you take liquid carbon dioxide, which is normally a bit less dense than seawater perhaps, and you get it down 3 kilometers, it becomes denser than seawater and wants to keep sinking. Now, normally there would be a concern if you made a pool of carbon dioxide lake at the bottom of the sea, it would eventually dissolve and mix in with the ocean and it would eventually come back up. But researchers that Tim describes in his book have actually analyzed and determined that by storing the CO2 in holes in the marine sediment, the CO2 is denser than the sea, so it stays in the holes. It infiltrates into the sediments, and then it forms hydrates, and the hydrates are solid. So these solid hydrates can stay in the sediment for millennia. And it's estimated that within the economic zone of the United States alone, we can store thousands of years of CO2, which is really surprising. Leslie?
Does this get around the concern you usually have with pumping CO2 in somewhere that when temperatures continue to rise, if temperatures continue to rise, there'll be a sudden release? Is this stable enough when it's done its dispersion here?
There is a concern with that, and it's a major concern for methane clathrates. CO2 clathrates have a melting temperature of 2 degrees Celsius or colder. Methane clathrates have a melting temperature of 7 degrees Celsius or colder, but there's far more of them. If you thought we had a lot of coal on the Earth, it turns out we have perhaps more carbon locked up in methane clathrates on the seafloor than all of the coal in carbon, all the carbon in coal.
That's a real loaded gun.
It is amazing. And what's even more daunting is that the USGS has determined that there are 73 trillion cubic feet of technically recoverable reserves of methane clathrates on the north slope of Alaska alone. And those are shallow methane sediments. So if you think about the Arctic Ocean warming, and you think about the warming shallow seas, people are already observing methane bubbling up offshore in the permafrost. This is a ticking time bomb. This is something we need to do about. It's a runaway feedback loop. I can't think of anything positive about it. They call them positive feedback loops. These are runaway feedback loops, and we need to address them early with techniques like Leslie's developing, the silica spheres that can keep it white and keep it frozen longer. We have to keep those temperatures down to keep those methane clathrates from going. Now, in the deep sea, at 3 kilometers or deeper, you have an enormous reservoir of cold water, and it is renewed each winter. So it's a very renewable resource. One of my advisors at Caltech, Richard Feynman, loved to say there's plenty of room at the bottom. And he was talking about scaling technology down to the nanoscale. I like to use it for the ocean. There is plenty of room at the bottom. That bodes well for deep sea water air conditioning. It bodes well for ocean thermal energy conversion. And it bodes well for utilizing all of the sea, the middle and deep ocean, to actually balance our carbon, sustain our seas, and ensure food productivity for decades to come. The second technique that Tim talks about in his book is another amazing technique, and this is a positive outlier borrowed from Mars. Do you know that the polar caps of Mars are not only water ice, they're also carbon dioxide ice. They're also dry ice, and they're seasonal. Well, it so happens that on the high plateau of Antarctica in the wintertime, you're within 30 degrees Celsius of the temperature at which carbon dioxide snows out of the air and onto the ground. And with a small addition of wind turbines down there, there's been a calculation done where you could actually build an air conditioner that would cool the air by 30 Celsius, and they could get up over a foot of carbon dioxide snow each night, each day, or I should say night because it's each 24-hour period during the Antarctic winter, accumulating feet upon feet upon feet of carbon dioxide directly on the cap. Cover it with ice, keep it cold, let it run all summer. I mean, in the summer it's just being reflected by the water ice above it. But you could accumulate massive amounts of carbon dioxide ice right there on the polar cap and perhaps do it sustainably. And potentially, I mean, the winds are enormous there. You could potentially do it all with wind energy. So there's another fascinating area that is potentially gigatons of carbon. In this case, physical, the physical sequestration of carbon. There have also been chemical approaches. Professors like David Keith at Harvard have looked at extraction of CO2 directly from the air. And then there are biological techniques, which I've been specializing in. At the Climate Foundation, we've been working on biochar technologies and associated terra preta on soils, and then the seas marine permaculture, with an eye towards food security. One of the questions today was, how do we afford all this? If you're just going to pile it up in marine sediments and there's no price on carbon, what can we do? Well, there are two approaches to that. And what I've learned as an engineer or technologist is that usually the technology is 15 or 20% of the problem. And for better or worse, more than half the problem is actually political, or building the political will to actually make a difference. That said, there are some very good groups that are working in this area. And just over the past 2 years at Climate Foundation, we've been strongly supporting the Citizens Climate Lobby. Why? Because they believe in a laser focus to develop a bipartisan solution called the carbon dividend. That carbon dividend puts a predictable and rising price on carbon. It's focused on a revenue neutral approach that's modeled after the Alaska oil dividend, which has been a very successful and popular program over the past 30 years in a Republican state. So here you have a Republican state that's got this incredible carbon dividend, makes a huge difference to the people. And the way it works is there's a levy charged on carbon at its source, and it's distributed on an annual basis to every adult resident of the state. Why not have a national carbon dividend? That's the question we're asking. It's our position that if the Republicans are really serious about electing a Republican president, they need to adopt and initiate a carbon dividend in order to take leadership on carbon balance. It's that important. And we think it's politically important as well. The social cost of carbon is measured $30 to $80, depending on your estimates, per ton of CO2. These are the social costs we're dealing with. The cost of real estate, of disruptions, of climate refugees. These are serious issues, and we feel that putting a price on carbon and doing it sooner rather than later can make an enormous difference in our lives. To that end, the proposal by the Citizens Climate Lobby starts at $15 per ton of fossil CO2 emitted. There was a study done by a very conservative think tank called REMI in Washington. And this study analyzed the economic outcomes of the carbon dividend. And the result was there was no economic argument against adding a carbon dividend. It was revenue neutral. It created jobs. It was good for the economy. It was good for the environment. And these are the kinds of tools that we need in order to actually make a change. Did everyone hear about the Keystone XL cancellation? Wasn't that an incredible result? I mean, there's a positive outlier. I worked for years with Bill McKibben against what seemed insurmountable odds. And yet to achieve this miracle, an overnight success 5 years in the making, gives us inspiration that principles like the carbon dividend can work. And so I would encourage all of you to get active with this. I'm actually a part of the Citizens Climate Lobby Mountain View chapter, which meets a few short miles away from here. They welcome student and other participation, and it's about getting involved and getting active. And so I would encourage all of you to check out Citizens Climate Lobby, because they are super focused on this one issue that is it's a rising tide that lifts all boats. People can choose they get a dividend check in the mail. They can choose to pay at the pump for higher priced gasoline or pay for renewable energy. But the non-carbon alternatives end up being far less expensive over time using this kind of approach. So this is something that we think makes a huge difference. There is something called border externalities, and that is countries that don't have carbon dividends. You have to reconcile that. That's already within the International Trade Organization regulations, the WTO. So it fits within that framework, and it honors those guidelines. In addition, technologies like biochar is a border opportunity. In this case, it's the border between the air and the rhizosphere, between the atmosphere and the rhizosphere. And that border externality is substantial. In other words, the third way represents ways that we pull carbon actively out of the atmosphere and we put it into soils and seas. And if we can certify it by independent third parties and say this carbon is coming out of the atmosphere and staying out, that's like a credit. That is a credit just as if we were here in the United States with a carbon dividend, producing low carbon products and shipping them overseas to countries that didn't have a carbon dividend. So those same border externalities are something that we can accommodate in the engineering sense into biochar technologies, marine permacultures, and other technologies that we've mentioned that pull carbon out of the atmosphere and into the soils and seas. So I see this as a key opportunity right at the intersection of politics and engineering. Half the problem is political will. The other half is system engineering. So this course is an engineering course. I'm going to spend more time on the engineering side. But it's important for us all to be multidisciplinary in the sense of understanding everything that needs to be done. And that sometimes means working on the political side as well as on the engineering side to actually get the problem solved. So we're faced with a collapsed price on carbon today. We're faced with cheap gas. And we have to consider food security for our own species and other species on this planet. How do we try to solve these problems in a scalable way, in a way that lets us build industries and scale to the gigaton level? And how do we can do it sustainably? Well, we have, in this case, solution one, solution two. I have first to talk with you about our efforts on food security on land. We've been developing biochar reactors in Terra Preta since 2009, so it's been 6 years. And we've gotten substantial support from the Gates Foundation and have developed a set of biochar reactors that can solve sanitation problems in developing nations and also in the United States, and can also begin to address restoring depleted lands. For 6,000 years, man has done a great job of turning forests into deserts. But it's really hard to turn it around, to actually take those deserts and bring them back to productivity. This February, I was fortunate enough to participate in the Urban Soil Conference in Los Angeles. And there at USC, or nearby, I had the great fortune not only to speak about biochar, but to meet some of the top soil scientists in the world. Alan Savory works in Africa and has studied restoration of soils. We had incredibly knowledgeable people about living soils. And it was fascinating to me to realize there is a critical mass coming together. And we actually have the understanding that we need to turn deserts back to productivity. Why is this important? Because there is a huge effect on the depleted lands in the United States. This is a picture of the biochar reactor containerized system that can actually provide sanitation for thousands of people per day, while at the same time generating sanitary biochar that can actually be part of the solution to restoring depleted lands. I keep talking about depleted lands. Why is this so important? I ran across a figure, and I have to double check the calculations, but Easter Island went from a population of approaching 100,000 people before Western man ever met them. And when Western man arrived, there were about 300 people left. What happened? They chopped down all of their rainforest. They were making these giant canoes that they used for hunting tuna fish. So they would make a giant dugout canoe. They'd go out, get the fish, and come back. But somebody chopped down the last tree. I don't know what was going on in their mind when they were doing it. The last tree was chopped down. It became grassland at best, but desert at worst. And they had to resort to cannibalism, food riots, you name it. And by the time Western man arrived, there were a few hundred people left on the island. The world will reach the population density of Easter Island in the 2020s. What does that mean for our entire planetary island? What does it mean? How do we actually avert the catastrophe that befell Easter Island? These are the key questions on my mind, and that's why we try to propel and motivate carbon balance in the context of food security. Why? Because we have billions of people to feed. We have close to 10 billion people on this earth already. There's an attempt to do what we call the soft landing, and that is to find a way to voluntarily manage our global population to the point where we can live more sustainably and reduce our numbers, because quite frankly, we've had such a pressure on the other 7 million species that how many more doublings can humans endure before we've wiped out most of the species on Earth? So these are the key questions that we need to try to address. This map shows depleted lands across the world. In red, you have the most degraded soils. In yellow, degraded soils. And you look at countries, including the United States, where we have degraded soils. I'm working in India with the Gates Foundation. Most of India has very degraded soil. And the question is, how do we return it to productivity? There's been thousands of years of farming there. And yet, the problem is, how do we return it to productivity? Well, from this conference, from this Urban Soil Conference, I've learned that there is a positive outlier. And that positive outlier is in the form of biochar, which acts like a sponge and retains water and nutrients, creates drought resistance. Biochar added to the base of compost is really fascinating because it improves the aeration of compost. The compost inoculates the char with effective microorganisms, including mycorrhizal symbioses, fungus, and that create dendritic nutrient pathways between the char that has buffered macronutrients and the roots of plants. And the plants then return sugars that are fixed in the fungus and actually increase the carbon. So that Terra Preta in Brazil is a growing, living carbon soil that 1,500 years later, you can pick up a piece of charcoal and look at the grains of wood on that piece of charcoal from 1,500 years ago. That's how permanent it is. Not only is it succeeding in being the richest soil in all of South America, accidental, by the way, it wasn't out in the fields, it was behind the kitchen window where they threw the charcoal, the fish bones, all kinds of waste. And 100 years later, maybe they noticed, oh, the weeds are growing better behind the kitchen window than they are out in the fields. So how do we recreate this positive outlier? See, once again, it's a matter of wandering around and noticing the positive outliers that can save the world. These are the accidental discoveries. These are the ways that major transformations occur day in and day out. Most of the time, it's by accident. And so keep alert for those little accidents of nature and man, those little positive outliers. So biochar is part of it. The third part is that those effective microorganisms end up adding to the soils. And so literally, it's possible to combine these effective amendments, these soil amendments, to restore depleted soils back to productivity and do what we call extensive agriculture. And by extensive agriculture, sometimes when you try to push on a rope, you just don't get a lot of results. And that is as you try to drive intensive agriculture to higher and higher yields and higher and higher productivity, you run into limits. Now, there are several definitions for extensive agriculture, but for me, it's about taking land that was used in the past and is no longer arable and restoring it to productivity. This is an opportunity for us to really make a difference in agriculture and ensuring food security on Earth. And at the same time, all that biochar that we're putting into the soil is staying for centuries. My good friend and partner, Johannes Lehmann, professor at Cornell, talks about biochar in the soil as soil capital. Soil capital because when you put carbon back in the soil, you're increasing the productivity of that soil for decades to come. So it's as if you're depositing something in a bank account and you're getting the interest coming off of that in terms of higher food productivity. So carbon levels are a great way, a proxy for thinking about soil carbon. An example are the Iowa cornlands. They started out before man's intervention at 6% carbon. Why? Because you had prairie fires and other things that inefficiently accumulated carbon over millennia. After 100 years of corn farming, we're down to 3% carbon in the soil. So it's still going, but it's not going so well. And guess what? In California, with 3 to 4 crops a year and all these rotations, we never let the soil rest, we're down below 1% carbon. So there's a huge challenge and a huge opportunity right here in our backyard. And that is, how do we get carbon back into the soil? How do we restore depleted lands? And how do we do it very efficiently water-wise? And that's the recipe that we have for restoring food security and food productivity. 1 gallon of gas is 19 pounds of carbon. The forest can certainly capture carbon. We've already altered most of those forests. And so the question is, can we ensure food security at the same time we're ensuring carbon balance? We think the answer is yes. And the way we address that is that half of the carbon may come off the land as food, but half of it remains as corn stover, as crop stubble, as agricultural residues. Many of those agricultural residues can be utilized. And if they're utilized in an effective way with a mobile transportable array of pyrolyzers that convert to biochar, we can get carbon back into the soil and do it efficiently enough. We're also using green waste. We're using municipal solid waste. We're able to produce chars from urban waste products that are sustainable, have low enough and have low metals levels, and also are eliminating pathogens. And so that opportunity to go full circle is a big deal. And char enters into macronutrient cycling. We're experiencing peak phosphate in our farming right now. We have a broken phosphate cycle in the United States. The phosphate is mined in Florida. It gets hauled to the Midwest where it grows corn. The corn gets hauled to, let's say, states like North Carolina where it goes and feeds pigs. The pigs poop. The poop goes into the Chesapeake Bay, and we kill the soft-shell crab, and we over-eutrofy the waters in the Chesapeake Bay. This is not a cycle. It's a broken sea. Biochar can come in at the pig level, even at the corn level, and we can take that phosphate, recycle it, get it back on the farm. It's about recycling phosphate. It's about recycling nitrate. Nitrate's a real problem because nitrate is soluble. When you put nitrate fertilizer on the ground and it rains, guess where it goes? It goes right into the groundwater. And in my home state of Massachusetts, my hometown of Woods Hole and Cape Cod, they're talking about spending $3 billion to wire up 100,000 homes with a traditional 1800 sewer system. What a crazy idea. That ends up being $20,000 to $50,000 per household to run an antiquated sewer system. And guess what? You're not cycling the phosphate, you're not cycling the nitrate. This is all because those septic tanks that they told us were so great, they may take care of the pathogens, they don't address the nitrate. The nitrate goes right into the ground, and it goes right into the waterways and right into the estuaries. So our challenge and our opportunity is to have that nutrient cycling. What does biochar do? Biochar has a very high cation exchange capacity. It adsorbs the phosphate directly onto the surface of the char. That attracts the mycorrhiza, it attracts the fungus, it attracts organisms that harvest. And what's more important is those organisms that take up residence on the char, they grab onto the nitrate anytime it's available, and they put it in their cells, and they actually effectively make the nitrate biologically insoluble. So when it rains, you don't lose the nitrate. The nitrate stays near the roots of the plants where it can go again. So now it's all about fertilizer efficiency. It's about reducing our carbon intensity. You know, more than 1% of the electricity in the world goes to produce nitrate fertilizers. So if we can actually focus on how do we use our fertilizer more efficiently, how do we ensure food security using these sustainable practices, we can go from a petrochemical fertilizer world, which is all about get addicted to fertilizers like you get addicted to sugar. You always need more and more and more carbohydrates if you're on an insulin cycle. It's like you're getting ready to hibernate or something. The same challenge and opportunity occurs with these soils, that if you have a dead soil that requires more and more and more petrochemical fertilizer each year, it's a vicious cycle. There's an alternative. The alternative is living soil that combines biochar, compost, and effective microorganisms. And it holds on to macronutrients near the roots of the plant where it's useful. And by the way, that compost and that char holds on to the water. During droughts, it's been demonstrated that plants with biochar do many times better than plants without during droughts, which is becoming an increasing problem in California and other drought-stricken regions around the world. So this is all about that cycle. Here's an example of that cycle. Every year on land, 100 gigatons of carbon is fixed by our land plants, and every year 100 gigatons rots. What if we could take just a few percent of that carbon and we could in fact offset it to char, put it back in the soils, increase our soil capital in those soils, and do that year after year after year? We'd be building up quite a bank account, wouldn't we? So that's a real opportunity, is to take part of this natural cycle and with a permaculture, in this case a soil permaculture, be able to do this. Now half of that 100 gigatons is in trees and forests. Half of it, let's say, is in man's agriculture. But that still may be about 60 gigatons of carbon fixation in man's agriculture. of which 30 gigatons may be crop residues, of which half of that's carbon, so that could be about 15 gigatons. And even if we are only 20% efficient at harnessing that crop residue, that's still 3 gigatons of carbon per year if applied at low efficiency on a global scale. And that's what we mean by gigatons of carbon balance in soils, is the potential is enormous if we find an inexpensive way to apply this on a global scale. And this is what we see as one of the major opportunities going forward. So biochar is graphene-based, disordered sheets of graphene that are very recalcitrant. They're high temperature. They can be used as a fuel, but they're better used as money in the bank in the soil itself. And it's, I've mentioned briefly, it can hold the carbon for 100 to 1,000 years. We built a first stage reactor in 2012. We demonstrated that at the US Biochar Initiative Sonoma conference with our team here. And then we went on to build a larger system. And this larger system is deployed in eastern United States, and also one of these is deployed with concurrent engineering in Bangalore, India. And I'll be flying there next week to work with our engineers on the ground in Bangalore, India, and then to attend the Terra Preta Sanitation Conference. Terra Preta means dark soil, dark earth in Portuguese. And it was these Portuguese soils that originally started the process. It appears to be effective in sanitation. It's also very effective in restoring food security and restoring soil productivity. And so that'll be the focus of that work. And it's really going from our urban waste environment to sustainable soils, that what this program is all about. We demonstrated in 2014 a system in Delhi. The system works by conserving energy very carefully, recapturing heat, and enabling the entire system to operate sustainably using the exothermal characteristics of the biochar production process itself, and using the gas that comes off as a vehicle to actually do partial oxidation. We developed a set of specifications for the system. I'd be happy to go over those in more detail with you later. And we see a number of potential revenue streams for the transportable omniprocessor, or TOP as we call it. And they include sanitation, tipping fees, biochar itself, producing energy, water, and agricultural services and products. So in summary, these are some pictures of the fair preparation, and we applied this technology not only in India, but also here in the United States. So we were funded through 2 rounds of funding with the NAFTA Commission for Environmental Cooperation. This organization is focused on what can we do across our borders in Mexico, United States, and Canada to actually make things sustainable. And it turned out that village, that Arctic village that Leslie mentioned earlier this morning, Kivalina, is a village that has no sustainable water system and no sustainable sanitation system either. And so we're hoping to address those issues. President Obama last month flew Air Force One directly over Kivalina, which you can see on this peninsula right here, landed in Kotzebue and met with the leaders there and said, this is something we have to address. If a foreign power came and took one of our towns, we would be up in arms about it. We would take up arms and we would defend our towns. And here we have a foreign power, the climate of the earth, taking one of our towns. This is something we have to address. We have to be proactive about. And it's one of the reasons that President Obama has put together the Clean Power Plan and the plan for how to address this kind of climate disruption. We're on the ground in Kivalina. We're funded and are winterizing the biochar reactor for operations in Kivalina. And I'm happy to say that we have community, tribal, corporate, and mine support and state-level support for building sustainable sanitation and transportable sanitation in the city of Kivalina that, quite frankly, will have to relocate. If you put a traditional sewer system in here and then had to relocate the town, you'd lose the entire capital. With this transportable sewage system and sanitation system, we'll be able to move when the town needs to move and make a more sustainable system. That's really a leapfrog technology, another positive outlier. Cell phones took over, and we never wired developing cities with copper because we had wireless phones. Why would we take a desert nation or a desert country and put in a sewage system that was designed for England in the 1800s? You know, there's been very little innovation in sanitation. Our toilet training stops at the age of 2. And our challenge and our opportunity is to really identify better practices. I never thought it would happen, but in my studies in this, I found a toilet far better than Western toilets. And it's this understanding of improving our sustainability to be able to go full cycle those nutrients, get rid of the pathogens, and address these issues sustainably. That's our challenge and our opportunity. It's finding those positive outliers. So let's switch over to looking at food security in the oceans. A daunting statistic, 94% of global warming today is in the surface ocean, in the form of a thickening warm layer of water that prevents the upwelling of nutrients and the sustainability of phytoplankton. Several papers by Behrenfeld in 2006 and Polovina 2008, 2009 have identified over the last century the decrease in plankton productivity over that time scale. They use Secchi disk data, which is when you would take a disk of black and white triangles, lower it down from a ship, and see how far down you could still see. And that's a good proxy for plankton. They integrated the Secchi disk database with the satellite database available in the last half of the 1900s. And they came up with some integrated plots of primary productivity across the entire world. What they found was that since 1950, the decrease in phytoplankton and primary productivity in the seas may exceed 40%. So we may have lost 40% of our primary productivity. Why is that so important? Because a third of all man's carbon that we've emitted over the last 200 years into the atmosphere has actually been absorbed by phytoplankton in the seas and is in the oceans today. So we've been getting a 33% discount. Now, if this continues, business as usual, pretty soon we're going to get all the plankton, all the carbon we paid for in the atmosphere, which is very daunting. And it's another example of a runaway feedback loop. And we have to be really aware of these runaway feedback loops, whether it's the plankton here or the methane in the Arctic Ocean, because these are the things that will trigger tipping points. And the tipping points may be points of no return. We call them event horizons, kind of like in the science fiction movies, right? If you get too far into a black hole, you cross an event horizon, there's no turning back. It's that kind of a tipping point we'd like to avoid and stay away from the event horizons that are going to make a huge difference. Plankton is one of those, and the question is, what can we do to keep us away from the event horizon of a runaway feedback loop where we lost that plankton productivity? And so that's what we look at in the oceans. Food security in the oceans. There have been a lot of fish in the oceans traditionally. We look to some of the most positive outlier in communities and ecosystems that we can find. And those, I love this community of kelp that we have just off the coast of California. Why? Because this macrocystis plant is one of the fastest growing plants on Earth. It can grow over 2 feet per day under optimal conditions. And it turns out it's not cold water that they need, it's high-level nutrients. So it's the upwelling of nutrients. You may have heard that since May 2014, the upwelling failed off the coast of California. The net result, we lost tens of thousands of pinnipeds, we lost millions of shorebirds, and we never got the upwelling and the productivity. It was devastating. And that's continued to this day. So we have a serious problem with primary productivity right off the shore of California. So the question is, what can we do to actually keep that system going at a time when it's so critical? So these kelp forests are some of the richest ecosystems on Earth. They live on a little ribbon of land on the eastern, let's say the western edge of the continents, the eastern shores of the oceans, where we get a lot of upwelling. And it's those ribbons that keep us alive. But as we get more and more global warming in the ocean, how much of the climate disruption that we saw off the coast of California was caused by global warming of the sea? And those are the key problems and challenges that we're trying to address with marine permacultures. What is a permaculture? A permaculture is understanding a natural ecosystem and adapting it as little as necessary to ensure sustainable productivity for humans as well as the ecosystem, living hand in hand with nature. And the opportunity to take a sustainable marine ecosystem and develop marine permacultures on a much larger scale is enormous. It's one that potentially requires no land area, no fresh water, no external input of nutrients, and yet sustainably, day in and day out, can restore fish, restore fisheries, produce kelp, and balance carbon. So I like to think of these kelp leaves as the world's most sustainable solar cell because they're self-assembling, they fix carbon, they store energy locally, they don't require any electricity, and they don't require any land area. So that's another positive outlier that I love to think about. And the reason it's so scalable, between here and China and here in Australia, there's 100 million square kilometers of untapped subtropical and tropical oceans. What could you do with 100 million square kilometers? We've developed marine permacultures that are resilient to shipping, container ships, aircraft carriers, and resilient to hurricanes. They decouple from the water when the waves get too steep and too big. The net result is it's sustainable. It can keep going. There's a company just south of here called Liquid Robotics. They're in Sunnyvale. They have successfully navigated a wave glider from here to Hawaii to Australia. And they did it using wave power, bidirectional satellite communications. It's a beautiful automated robot. We hope with our marine permacultures to build the world's largest robots that will navigate the 7 seas while sustaining the oceans and building and scaling this beautiful marine permaculture of a kelp forest on square kilometer scales, traversing the seas and to be harvested at regular intervals. Kelp is a billion-dollar industry. You can produce alginate, carrageenan, not to mention habitat for forage fish. And forage fish is some of the best protein that you can possibly eat in terms of health, sustainability, omega-3 fatty acids, incredible benefits. So we're seeing this as a very scalable approach. And I love this picture of the Earth where we realize we really are the water planet. This is our opportunity to start utilizing some of those underutilized resources. Here's this wonderful kelp leaf solar cell vision. And I think that scaling this type of approach is really a key opportunity as we go forward. From the video, which you may have seen, we have this notion of an oceanic fish springs. The 99% of that ocean surface is aquatic desert. That aquatic desert is a nutrient desert. The nutrients are a mere 500 meters below the surface. And those few hundred meters that have to be traversed have an energy barrier. That energy barrier is thermal. The cold water is denser than the warm water at the surface. How do we solve that problem? Well, we can use wave energy, an average of 2 meters waves across the Pacific Ocean, and a flapper valve and a long cable to upwell nutrients to the surface, as we demonstrated in the last decade off Hawaii. That system still has a challenge that you have cold water near the surface. It'll sink back down and go away. So we demonstrated that it could be done. We had a beautiful natural validation of this work in 2008 in our work with the University of Hawaii. After 2 days of operation of the system, we came back 2 weeks later, and this 17-foot-long whale shark was still circulating the ocean pumps, eating all the phytoplankton that we'd produced. So it's this beautiful natural validation. I couldn't have written a script like this, but it happened all by itself. In this case, nature was telling us we're on the right track. There were, in addition, forage fish, game fish, in amazing concentrations around this oceanic pump system, and that was the inspiration to extend the system. Since then, over the last 3 years, the Woods Hole Oceanographic Institution, the Marine Biological Lab, and NOAA in Woods Hole, at the Climate Foundation, we've been developing marine permacultures with this task force. The notion is to take the original system of a wave-driven pump, a valve, and a way to get that water up to the surface. We pass it through a heat exchanger, and that heat exchanger warms up the water to within 2 degrees of the surface. We found something very interesting about subtropical waters, and that is the surface waters are actually saltier than the deep water. Why is that? Because there's evaporation at the surface. You have a lot of sunlight, there's evaporation. 1 part per thousand saltier. What does that mean? It means that we can actually solve the problem. How do we do that? The fresher, colder water goes up to the heat exchanger. The heat exchanger, with an approach temperature of 2 degrees Celsius, means that the thermal difference, well, the salinity difference can overcome the thermal difference. And even though the water is 2 degrees colder, it still floats. The net result is that when we use diffuser pipes and we release the water to the kelp forest, the high nutrient water floats to the surface. When it floats to the surface, it fully irrigates the kelp, and whatever's not used by the kelp is used by the phytoplankton, and those cyanobacteria we were talking about earlier today actually can do their work and restore productivity and actually provide food for forage fish. So now we have food for forage fish, we have habitat for forage fish in the kelp forest themselves, and we can grow a square kilometer of kelp forest. Personally, I'm looking forward to diving on these kelp forests because it'll be warm, 100-foot visibility, and tons of fish. Forage fish, game fish, sharks and tuna fish. You name it. It's going to be a wonderful future. And so we see an opportunity to develop ecotourism in this area. And that is, who wouldn't want to go diving on a pristine kelp forest that's beautifully warm and good visibility? This kelp forest in plan view looks like the bottom array. These heat exchangers would be an array of tubes that would actually disposed at a depth of 25 meters, which is below the depth of all the shipping. And the kelp forest then would operate here. We envision drag plates or steering mechanisms that enable left-right operations. In fact, research has been done in New York on the steering of these mechanisms in mesoscale eddies. It turns out at any given time there's 100 mesoscale eddies traversing the Pacific Ocean. These mesoscale eddies are like little storm systems. They're highs and lows. And if you put not one but several of these systems in a circle the wagons, so to speak, they can actually provide nutrients to each other. And this is a key opportunity as we go forward to be able to create trains of these systems that can actually sustainably produce fish and be harvested at regular intervals.
Brian, I know from past weeks that they will cut us off fairly close to the formal end of class.
At 50 minutes after the hour?
Yeah.
Very good.
Before that happens, I'd like to ask, I'm sorry to interrupt, but
Please.
Are there any questions people didn't ask, didn't get answered? All the ones that you asked by email got answered in that link that I emailed around. But are there any questions anybody's dying to ask while we're here, while your compatriots could see it on video? Any burning? Okay, good.
That's great.
Then in that case, you've got it till.
So we've developed some mechanical engineering on how to effectively convert wave energy to the actual system itself. We have some designs that include wave action cables connected to the valves. The valves can be double acting. They can work on the way up and they can work on the way down. And the notion of one-way flapper valves, oops, let's see if this is working. This one-way flapper valve, on the upstroke, the top valves are opening, and on the downstroke, the lower valves are operating. And that result is you get twice as much pumping. So we envision being able to pump hundreds of thousands of cubic meters of water per day. And we ran the calculation and ends up, I'll have to look at the figures again, but the calculation was on the order of 60 tons of biomass fixed per day, or produced per day, on a system of this size. So several hundred thousand cubic meters of upwelling. So it ends up, it looks very scalable. The kelp, as it turns out, doesn't require cold water. It requires high nutrients. And it turns out California kelp thrives in 20 to 25 degrees Celsius water. And Baja kelp optimally grows at 25 to 30 Celsius, which is wonderful. It's exactly the temperature of the tropical waters that we're seeking to go into. So as long as we can provide the nutrients, we can sustainably keep the system going. In addition, there are two other sources of energy. One of them are the currents of the mesoscale eddies, which can approach 20 centimeters per second differential between 25 meters and 500 meters depth. And secondly, the Stommel salt fountain, which in 1952 was determined to be a way to actually perpetually run a system in these areas of the ocean where you have salinity differences. Warm salty water can be denser than cool fresh water, with the net result that there's intermingling of the waters themselves. These are the regions of the world that are most amenable to this type of salt inversion. Many major parts of the ocean are amenable to that. And here's an illustration showing the sinking salt fingers and the rising fresh fingers that work on a very small scale as well as larger scale. So this is a vision of a salt fountain effect. The energy levels are smaller, but in doldrums or other conditions, it's a third form of energy we can harness to do the upwelling without requiring external energy sources. In addition, Phil Yecko from Cooper Union in New York has research conducted on robotic geophysical fluid dynamics, and that is how do you get robots to sustainably navigate the 7 seas in mesoscale eddies and station keep, actually, without any external use of power, just using the currents themselves, be able to navigate into and out of these mesoscale eddies and stay where you want to in the ocean. And that's a key sustainability opportunity as we see going forward. Some experiments have validated the results, with the results indicating that it's quite feasible and amenable. And here's a beautiful picture of the liquid robotics wave glider crossing the Pacific Ocean, which we see as a vision for the future. We just need to scale this up by a factor of 1,000. And that's something we look forward to getting your help doing. Please feel free to reach out and join us in any of these efforts to try to make a sustainable difference as we go forward and truly try to make a difference. So I'd like to say, live lean and prosper. And I think it's all about living sustainably. And thank you very much for your attention.